Okay, now we will see the types of relations. As we have seen that relation is a subset of Cartesian product of A cross A, and where A is a set. A is a set, and what is the definition of a set? A well-defined collection of objects called a set. A well-defined collection of objects. Okay, so this we studied in the previous class. So DNA of this relational function is a set, means it starts from sets, then Cartesian product, then subset of the Cartesian product. So this is the main thing that you have to remember. What is a relation? Relation is a subset of the Cartesian product. And generally we are taking in our course 12 A cross A, a relation on set A. Now we have types of relations. In our course, we have three types. We will study the three types of relation and their question. But we should know some more types. Like number one, first relation is empty relation or empty, or is also called as void relation. Empty or void relation means obviously the relation will have the Cartesian pair. Cartesian will have ordered pair which has nothing, is zero. So if the relation is called empty if no element is related to any element of it. Okay. So relation R is the definition. Relation R in a set or on a set A, on a set A called is called an empty relation. And empty relation means if it has null set. If no element of A, if no element of A is related to any element, is related to any element of A, related to any element of A, that is what we will denote. R is a null set. This you know that R is a null set, is a subset of A cross A. Okay, null set is a subset. For example, if we take A is a set of numbers that have the numbers 1, 2, 3, 8, 10, and 11. Okay. Then A cross A must be 1, 1, 1, 2, 1, 3, 1, 8, 1, 10, 1, 11, 2, 2, 1, 2, 3, 2, 8, like that. It must keep in your mind. And R be a, let R be a relation defined by R is a set of ordered pairs A and B, and they are related by A minus B is equal to 4. A minus B is equal to 4. This is the relation which is defined on this set. But if you see that 1 minus 2, 1 minus 3, 1 minus 8, 1 minus 10, 1 minus 11, 2 minus 3, 2 minus 8, 2 minus 10, 2 minus 11, 3 minus 8, or 8 minus 3, 2 minus 8, not because A is first element. So you will not get 4. There is no number here which there is no pair, ordered pair where the difference is minus 4. Okay. So therefore it is R is empty. Therefore then R is an empty relation. R is empty. R is an empty relation. finite relation. Okay, so got it? If it is defined like that, we can say it is an empty relation. Okay, and next is second type is now universal relation. Universal relation. Say for example, A is a set of voice sections, and if we say the relation is A is A is a, means the relation defined by the number of girls or something like so, then it will be an empty relation. So similarly, now that is empty. Now I'm going for universal relation. So in universal relation, you must be understanding that relation which is full, having all the possible ordered pairs of the set R of the Cartesian product of set A cross A. So a relation R on a set A is said to be universal relation if each element of A, if each element of A, each element of A is related to every element of A. Each element of A is related to to every element of A. Every element of A. That means this relation will be equal to the Cartesian product of A cross A, then it is universal relation. It's the biggest relation. For example, we can take let A be a set of elements, is the set of elements 1, 2, 3, 4. Okay, and the relation is defined as RB relation, which is defined as set of ordered pairs where the difference of two numbers, mod of the difference is greater than equal to 0. The difference of any two numbers, difference of any two numbers will be greater than equal to 0, obviously. Okay, 1 minus 1 0, but 1 minus 2 will be greater than 0, all other will be greater than 0, so it will have all the ordered pairs of A cross A. Then R is a universal relation. R is a universal relation. Okay. Then third type is identity relation. Identity relation. Identity relation, if each element of A is related to itself only, means 1 1 2 2 3 3 4 4, then it is called identity relation. The relation R on a set A is called an identity relation. Identity relation if each element of A, if each element A is related to itself, is related to itself. And it is and is denoted by IA because we are taking set A, so IA, and it is a relation R, and this will be equal to AA 112233, where A belongs to A. Okay, A belongs to A. For example, let A be a set of elements 1, 2, 1, 2. Then identity relation R, if R having the elements 1, 1, 2, 2, all elements 1, 1, and 2, 2. Then is an identity relation is an identity relation is an identity relation. But if any other pair will come, then it will not an identity relation. If it will be 1, 1 and 2, 2 and 1, 2, then is not an identity relation. Then it is not an identity relation because 1, 2 is extra. All the numbers should have their doublets. You can say doublets. In throwing the dice, we have seen the doublets. So doublets should be only there when it is an identity relation. If any other ordered pair will come, then it is not an identity relation, not an identity relation. So keep in mind these are the basic three relations. Now we have in our course actually there are three relations which is given in our syllabus especially. So these relations we will see what are these relations. Number one is, and we have to do the questions on this one, reflexive. First is relation, reflexive relation. Second is symmetric relation, and third is transitive relation. Transitive relation. So reflexive, we will write the definitions later on. First, we will try to understand what are reflexive relations, and very important thing. Let us take one example. Let A is a set of elements 1, 2, 3, 4. Okay. So definition first. Do you know this sign? For all A, B belongs to A in reflexive relation. For all A, B belongs to A. But here A, B, we will take only A because here A will come. So no need to take A, B, not different elements. Here it should not be the different element. So keep in mind here we will take A belongs to, for all A belongs to A is every element. For every element here it is very important for all. This is the symbol used for all. For all A belongs to M is for all elements of A. Okay, A belongs to A. A belongs to relation R. Then it is called reflexive relation. For example, its reflexive relation. If I want to write its reflexive relation, it should have 1, 1, 2, 2, 3, 3, 4, 4. If 4, 4 is not there or 3, 3 is not there, then it is not reflexive. For reflexive, every element you should have all the doublets. You can say all the doublets should be there. If anyone is not there, then it is not reflexive. This is the main point for all because this will not come in symmetric and transitive. So 1, 1, 2, 2, 2, 2, 3, 3, and 4 4. 3 3 and 4 4. Then it is a reflexive relation. Okay. And symmetric relation is for any two for A and B belong to, for any pair A and B belongs to A. If we take any pair A B, okay, for the two pairs, every possible pair which is in the given in the relation, they should have, like, if AB belongs to A and AB belongs to the relation, if A and B are related to R, implies that BA will also related to R. BA also there in, means if 2 1 is there, 1 2 must be there. So AB, if we take suppose 1 2, 1 and 2, let's say 1 and 2 belongs to A, then R must have 1 2 and 2 1 both. So then R will be having 1 2 and 2 1. Then it is called symmetric relation. So here, no, the important thing, we are not using this for all. Means for, we will not see that for all elements 1 1 2 2 1 1 3 3 1 1 4 4 1. No, no. Just you check the relation. Here you can see that how many elements are there, and for that element there should be a combination. For example, if we have one more element, suppose 3 is also there. So we have 1 2 2 1, and 2 3 belongs to this, then 3 2 must be belonging to this. Okay. So 2 3 belongs to this, 3 2 is also there. Then it is a symmetric relation. So hope you understood. It is not necessary for the symmetric for all elements. It should be the for all elements. But here for reflexive, it is necessary that all elements should be related to itself. Then it is reflexive relation. Then it is reflexive. Okay. We can take many examples for reflexive and symmetric. And transitive is just like it is just the, we can say the example, just for example, A likes B, B likes C, then A, then implies that A likes C also. Like that only we have, means if three elements, it is for three elements, or we can say A B C, for A B C belongs to A B C belongs to A B belongs to R, and and B C belongs to R. If these two belongs to R, then it implies that A C must belong to R. Then it is transitive. Okay. Uh, for example, if 1 2 is there and 2 3 is there, then 1 3 must be there. Are you getting my point? So then it is transitive. Here also it is not necessary for transitive that all numbers should be there. We have to check the transitivity, reflexivity, and for example, we check that it is transitive or not. For suppose A is a set of elements 11, 12, and 14. Okay. And R is a relation which is having the ordered pairs as 11, 11 and 11, 12, 11, 12 and 12, 14, 12, 14 and 12, 12, 12, 12 and 11, 14, 11, 14. So for transitivity. We are checking for transitivity. This is the we are taking the transitivity here, taking the transitivity. So if we take 11, 11, and it is ending with 11, 12. So 11, 11, 11, 12. So 11, 12 should be there, but 11, 12 is not there. 11, 11, and 11, 12. 11, 12 is also there. Yes, is there. So 11, if you check 11, 11 and 11, 11 belongs to R. First, we take this combination 11, 11 and 11, 12. 11, 12 belongs to R. Then it implies that 11, 12 must belong to R. Then 11, 12 must belong to R. 11, 12 is the itself this one. Okay. Okay. First combination. Then we can take 11, 12 and 14. 11, 12 and 14 means 11, 12. Now we will take second set 11, 12 belongs to R, and 12, 14 belongs to R. 11, 12, 12, 14 belongs to R. So this implies that 11, 14 also belongs to R. 11, 14. So 11, 14 is there. Yes, correct. So like this, we will check all the possibility. 12, 14, 12, 14 is there, but 14 is not there. So we will not check this one. But 12, 12 is there. So 12, 12 is also always itself. Because 12, 12 here also 12, 12 you will write. 12, 12 you will get. 11, 14 is there. 11, 14. This is 11, 14. Yes. 11, 14, and then 14 something is not there. So we will not check this one. So we have seen that these all are belonging other than that. So therefore it is a transitive relation. It is what? Transitive. Transitive. Means we will check if the second element again is at the first position. Means AB, if AB is there and BA is also there, then we will check the transitivity. Otherwise, we will not check for 12, 14. We will not check for 12, 14 because and 11, 14 also no need to check. Only we have to check 11, 11 and then 11, 12 and 11, 14. Then 11, 12, 12, 12 or 12, 14. That's it. And 12, 12 always 1, 1, 2, 2, 3, 3. They all are transitive because 1, 1, then 1, 1 again we can write. So same thing will happen. So like this we can check the transitivity, reflectivity, and symmetric relations and check and find out. We will take one example. Okay. Question, we are taking one question, extra question. You will understand more. Show that the relation, the question is show that the relation are on the or in the set 1 to 3. 1, 2, 3. Okay. Defined by or given by R is equal to the set of ordered pairs 1, 1, 2, 2, 2, 2, 3, 3, 3, 3, 1, 2, and 2, 3. 1, 2, and 2, 3. Okay. 1, 2, and 2, 3 is reflexive. It is reflexive so that it is reflexive but neither symmetric, but neither symmetric nor neither symmetric nor transitive. One more thing you have to check, it is not necessary every time you have to take each and every element, but here it is starting, so we are taking. If it is reflexive, we can, okay, here we have to do because it's very simple question. Otherwise, if we examine and we will find that it is reflexive, so we can directly write here from the definition that for all A belongs to A here, for all A belongs to A belongs to R, therefore R is reflexive. This is also enough. But here we are taking some examples. So reflexivity, for we have to check reflectivity or reflexive relation. So or for checking reflexivity, here how many elements are here? Here only 1, 2, and 3 belongs to A. Okay, and 1, 1, 1, 1, 2, 2 is also there, and 3, 3 is also there. Okay, 1, 1 is also there, 2, 2 is also there, 3, 3 is also there. So all are there belonging to R. So now that is, we can say that now for all A belongs to A belongs to the relation R, therefore R is reflexive. So generally when it is reflexive, we can take the example, or if it is not reflexive, then we have to compulsorily take one example which will show it is not reflective. Like we are going to do the symmetric relation. So when we are doing, it is not symmetric. It is not symmetric, then we have to take one example. As I told you, we have to find out 1, 1, 2 to leave it. We will take 1, 1, 2, 2, 3, and 1, 3 is not there. We can take these two, this one. 1, 1, 2 is there, and 2, 3 is also there. So 1, 3 must be there. It is not there, so it is not reflexive. This example we will take here. 1, 1, 2 belongs to R, and 2, 3 also belongs to R, but 1, 3, 1, 3 does not belong to R, does not belong to R, does not belong to R, which shows that therefore R is not symmetric. R is not symmetric. Third, we have to check the transitive relation. So for transitive, also you have to take. Sorry, this I did transitivity. I think. Yes, this I did transitivity first. No problem. This is transitivity. So this is, I did transitive A B B C. Now reflexive. Reflexive means A B belongs to R. B A also belongs to R. So reflexive. Sorry, what I am doing. Symmetric. Symmetric means A B belongs to R, implies that B A also belongs to R. So for symmetricity, 1, 2, you can take here 1, 2. 1, 2 belongs to R, but 2, 1 is not there. 1, 2 is there, 2, 1 is not there. 2, 3 is there, 3, 2 is not there. So we can take this R, but 2 1 does not belong to R. Okay, therefore R is not symmetric. Okay, so any given relation, if it is symmetric, transitive, and if it is symmetric, transitive, and reflexive, then it is called equivalence relation. It is called equivalence relation. If it is here, it is not an equivalence relation. The equivalence relation, if it is reflexive, symmetric, and transitive.